Excellent. All right, welcome everybody to this week's Geometry and Model Theory seminar. Our speaker is Vincent Grandjean from Fortaleza, and he is going to tell you, as he tells me, about Lipschitz trivial values of polynomial mappings.
Yes, mappings would have been enough. Yes, thank you. Okay, so I'd like to first praise the choice of the organizer of the event in selecting their speakers. Lucky for you, lucky for them too. So thank you for giving me the opportunity to talk. I'll just make a comment before starting the math. So Maria's last week had a very short seminar, and we need to make good use of resources which are given to us. So we have 50 minutes every week, probably last 15 more minutes. So there is a likely possibility that this not yet wasted 15 minutes might be used today, okay? Right. Where do I start? I will start with some definitions and a context. Okay. So what I want to present today is a result of a trisingularity of some sort. The result in a very informal way. So if you mix two very different rigidities, then you're going to have no surprise. That's what the statement somehow says. So let's start with a mapping. Okay, so I'm going to define some properties, and some properties makes only sense only if you add hypothesis on the mapping. So I will not precise them because they're clear. So most of the math I'm going to use today, they are of the undergrad level. All definitions I'm going to present, it's mathematics we can meet when we are undergrad students. But for using polynomial mappings, it's topology or differential topology. So I will say that the mapping F is a proper map if the image of any compact is compact. So in particular, this means my guys have a topology. Okay. Doesn't need to be continuous, but just that. What else? Now, I will localize this version. I would say the map is proper at a subset of N. And since there are people with a huge background in logic, I will not want to mess up with the empty set. So I will consider that Z is not empty if I can find a neighborhood of Z and such that the restriction of phi to the pre-image of V into V is proper. So I will use proper at Z, locally proper at Z, things like this. In particular, I can define J phi, so the yellow next set, which is the set of non-properness value of the mapping. I'll come to this set later on, but it's the right moment to present it. Non-properness values of phi. In particular, this is all the set of all values at which the map is non-proper. So a stupid observation. So if I pick a value which is not in the closure of the image, this pre-image is empty, then it is proper. Okay, so this is okay, so stuff like this. So the set of non-properness value is contained in the closure of the image. All right. What else? Yeah, okay. What else afterwards? Let's take page 1. So now, as I said, topology and differential topology. assume that f is ck, so which means I'm working with manifolds now. So I will write this for the set of critical points of the mapping. And I'm more interested actually at the critical values. These values of the critical points. I'm particularly interested in this set. So now, so these are mostly what I'm going to use during this this talk, and the notion of Lipschitz, but this I will not recall. I think it's obvious. So what it is, roughly speaking, I want to talk about. It is, I want to I'll talk about equisingularity. Equisingularity, it's a way to say that I can say that a family of subsets is locally trivial, is locally a product. So in that sense, they have, if they have singularities, they have the same singularities. So more precisely, I want to know if when I pick a guy, I pick a value in N, I can find the neighborhood of this value in N, a map which is, I'm going to explain this. So here I have phi, and here I have the projection onto V, which is an isomorphism. I will precise what I mean by isomorphism. So, but there is a category in which we are working, so isomorphism might be clear at this stage. With some prescribed regularity. And the same regularity is isomorphism, and regularity can be discussed. Okay. So since I have chosen topological context, I will say, sorry, I will say that isomorphism, oh boy, that's going to be something like a homomorphism or a diffeomorphism. And regularity is much more flexible, depending on your setting. Can be continuity, ck for some k, and k can be very, can be in N, finite differentiability, infinite differentiability, or even, you can even require sometimes being analytic. Okay. You can ask also that it is Lipschitz, which is something weird, it's a weird notion, or definable somewhere. You may want also to consider isomorphism, which are definable in no-minimal structure, expanding real numbers, which fits within the context you have decided to be in. Okay. Now, of course, I can't read my notes, but this is not new. What? Okay. There is a general principle. So why should I continue? I mean, it's not a principle. It's a heuristic principle. It's what we can prove. Now, assume that phi is definable, and I'm not going to be as being. So I fix a no-minimal structure expanding the real numbers, and a big definable map, which is enough regular. So regular might be C0, C1, CK, C infinity, or whichever you want. And the principle is just that I forget to vocabulary. In which case I will say phi is C trivial, is trivial at C. I mean, it's I get my regularity, which is given is regular trivial ends. Geometrically speaking, it means that over the preimage of this neighborhood, I have a fiber bundle structure. I have a model fiber, and I have a prescribed regularity. So homomorphism, definable homomorphism, C1, CK, whatever. So what I want to look at is when I can have this fiber bundle structure over a given value. And so general principle with definable maps, whenever they are continuous, is that most values are P is trivial at most values. This is the general principle. Of course, the way you are trivial will depend on your initial conditions. But even working in the topological category, just with continuous map, you can have this. If you're on continuous and definable, it's more work, much more. It's most values. So what does it mean? It means that the set of trivial values, at which time is trivial, contains an open dense definable set of n. Of course, if the image is very small, that is of positive codimension, most values are empty fibers, but I will consider the empty set with this fiber bundle structure. Okay, so this is a. So this case is clear. So now what is interesting is when the phi somehow fills some part of the space n, and when the image contains an open set. And yet, even in this case, this heuristic principle holds true. Okay. So, right. So this you pick at random a value. It's from the point of view of triviality, it's a boring value. There's nothing to say. All the nearby values are from this way of treating them. They're all the same, and as a bundle, the bundle of values actually have structure of fiber bundle. But I will present the last definition. That's the one which is going to matter today. So now assume that just I have a map between metric spaces. Okay. So now I'm throwing a metric structure within my data. And I will say that the map is trivial at the value C. It's running too fast. If I got the scheme over there, okay. But here there's some precision. I get this homomorphism. There is such a homomorphism. Okay. So I have this bundle structure again, fiber bundle structure again. I mean locally fiber bundle structure, which is Lipschitz. Okay, so it's a homomorphism which is Lipschitz. But here I have to precise. Here is more or less clear what it is, which metric. And what I want that phi minus 1 of V is equipped with the restriction of dm. So it comes with this metric. So the restriction of the ambient metric to the subset. So I measure the distance between points of this in n. Okay. But the more interesting one is here. The metric I will have here is the product metric. So that's going to be, if I have to write it in a complicated way, write it this way. It's a Riemannian way, that's going to be this way. That is the distance between 2 points here, just the sum of the distance of the 2 points here, projection here and here. Okay, that's all it is. Okay, so now I can start talking about results. So this is all the things I'm going to use today, all the notions, well, almost. So main results. Before given the statement, I just want to point out an obvious fact. It's whenever my space M is not compact, this condition is very, very rigid. If I work with if I was working with C1 triviality, I have locally Lipschitz. But usually the map realizing the trivialization is not globally Lipschitz. And so which allows lots of flexibility, actually. Here, I ask that this map is P-Lipschitz. That is, there are a constant which is global for all points in there and in there. And if this guy is not compact, that is somehow you can speak of a notion of infinity. And that is something like I could compactify, and when I go close to the boundary of the open set in the compactification, being Lipschitz is a very, very strong condition. Okay? Very strong condition. It's much stronger than, in some sense, as the result we'll see for polynomials, much stronger than being C1 or C infinity. Okay, so what I'm going to play with today is polynomial map. Polynomial mappings and over either real ones or complex ones. So far, this is only these are only notions that you can see at an undergrad level. Okay, so the theory is the fiber bundle maybe need a little bit of a sophisticated topology, but it's possible. So the first result regarding polynomial and this strange setting of Lipschitz trivial values, which never been treated. I mean, at least as far as I looked for in the literature, there's nothing about it, absolutely nothing about it. Well, there is quite a bit of work and about this. Okay, and you're going to see why. So the first result we get, and which is the motivation of today's talk in this setting. So these are obtained with my Brazilian colleague, Alexandre Fernandez from Fortaleza. Humberto Suarez from Teresina. And this we found in 2018, published 2 years later. And it says something about the rigidity. So pick a complex polynomial function. Okay, a function. Then, and suppose it's not constant. I mean, it doesn't matter. So if f is trivial at this is Lipschitz trivial. At the value c. Okay. So that works also for constant function, for constant polynomial, but they're not very much interesting. Then that exists a linear change, a C-linear change of coordinates, and a polynomial in one variable, such that f of x1, so after a change of coordinate, is that. So you only have polynomial in one variable, which essentially are polynomial in one variable. So a guy like this, the only level it has are union of hyperplane, parallel hyperplanes. That's it. So that's very peculiar. So in particular, that implies union of parallel hyperplanes if not constant. Okay. Very weird. It's very, very weird. It's not very interesting. So there are nothing interesting here. That's what it says. So this, and to some extent, if you played with families of levels of polynomials, when you draw them, you see that at infinity they get very close to each other. And this condition here, somehow I will return to this, say when you take two different levels, they have to be far from each other. And now you say, okay, so now I got polynomial levels, and they can't be close to each other. So the only example you come with is just, it's going to be parallel affine subspaces. Are there any others? Well, the truth is, just in the complex case, as I'm going to see, no, there's no other. This, I mean, as I'm going to state. Okay, so let's give some the proper statement now. Ooh, already page 3. Good. The proper statement. I need to introduce a further object, which is, some people call it the tangent space at infinity, tangent cone at infinity, but I will name it otherwise. So I pick a subset in my Euclidean space, okay, whether it's real or complex. And I will close it in the projective space of a K of dimension n. And I'm interested in the closure in itself, what the extra points I get. Okay. That's the intersection of the closure with the hyperplane at infinity. Okay, so there's nothing surprising. In particular, this set is bounded if this is empty. Okay. X bar. And I will call this set the asymptotic set of X. In this case, it's clear it's at infinity. You can do the same at the point. You just blow up the point and you get the same sort of limits. When you take the closure of the subset you consider minus the point you're going to put. Okay, so now what do I do with this? Okay, so I'm going to quote the result we have with, so this is the part of the PhD of a student that I share with Maria Mielska. His name is André Costa. And Maria Mielska. And this is a still warm result. Let's say we get this at the end of last year. So it's a, let's consider a polynomial map. Okay, polynomial. So I'm going to pick a value. So KP, and I will write dimension of its asymptotic set this way. N minus 1 minus m. What interests me is the codimension, is m. And it's the codimension in the hyperplane at infinity. Okay. In particular, if this I can allow this to be minus 1 to mean that the fiber is compact. Okay.
What is n?
That would be the codimension of f minus 1 of this. It's a codimension. Okay. So if it's empty, I say that's codimension n in the hyperplane at infinity. That's what it would be. Anyway, so the result we have is the following. The mapping F attains, this is important, the Lipschitz radial value C, whoever it is, if and only if there exists a polynomial map from Km, this M. Let's do some pedagogy, okay? With colors. The same in KP, so polynomial. There exists a linear projection from Kn into Km, which is linear and surjective. It's K-linear, of course. So it's the same N, such that, well, first, the function f, as in the previous case, depends on fewer variables. What it means is just depends on m variables. Yes, depends on m variables. Okay. And moreover, and the value C is a regular value of properness. So it has two properties of G. So if I have a Lipschitz radial values, I can kill off many variables, maximal number of values, find a polynomial in these fewer variables, which coincide with f everywhere. And when I extend it, when I suspend it this way in Cn or Kn, and such that this value C is a regular value of the polynomial map, the new polynomial map, and also the level G minus 1 of C is compact. That's what it means for a value to be a proper value of a mapping. That means that the corresponding level is compact. Okay, so it's a very, very strong property, and which is what the statement here. What are the level of the polynomial in one variable? They are just unity many points, which is compact. So it's the generalization of this. Here we just have complex one, but here it's real and complex. And moreover, so if I am in a complex number, I can show that actually M is equal to P. Okay. And G is dominant. So what does it mean it's dominant? It means that its image is dense. That is another way to say it is just it's a generative finite mapping, which is almost subjective. I mean, that's just so the fibers of a dominant map from CP to CP, they are just unit of points, and of course there is for generic points in CP there is a bound which is constant, because the set of bad points is going to disconnect. That's not going to disconnect the state of the site. Yes.
K equals R, so the dimension may be different.
Ah, exactly. I'm going to give a. We don't know much about K equals R because it's more flexible, and so now I need to do something. Yeah, I think this is accurate. Do something. It's hard to guess what would be this dimension. I will just. We don't have good example in a real case. I'll just continue here. Okay, so nice 7. So what is this Motzkin polynomial? That's over there. So I'm going to introduce something here, which I should have introduced earlier. I introduce LF, the set of Lipschitz trivial values of F. Okay. So I'm not going to answer your question, Jean-Philippe, because they're always too hard anyway. But I can somehow supplement a few facts. Okay. Motzkin polynomial is just in that regard interesting polynomial which okay, oh no, not yet. Okay, let's be obvious first. So whenever I have a map like this, which is polynomial, the fibers are never compact. So F minus 1 of C is either empty or unbounded. And this is implied C cannot be a proper value of the map. C proper value, this cannot happen. Okay. Well, it is obvious, in fact, that complex algebraic sets of positive dimension are not bounded. They go to infinity. We know it's not true for the real ones. Huh? Just take the simplest one is just the square of the distance to the origin. All the levels are the spheres centered at the origin, so they're all compact or empty. So this is trivial. So here I have special value, it's a critical value, and here I have, I'm not mistaken, that should be square root of t, which is compact. So very different phenomenon between real polynomial mappings regarding the topology of the fibers, the possible topology of fibers, and the complex one. So now I can speak of the Motzkin, which is so here I would have so what do I have here? I get GF equal 0, which is equal to the critical value, and LF is the rest. In this case, that would be that. Okay. But so Motzkin polynomial, the polynomial that's going to combine all these phenomena. Something like this. I need to see the constant to get the, of course, yeah, this is wrong. This guy, this way. So we can check the following, that it has two critical values. You can check that the set, whenever you pick a level which is in there, it's non-compact. And you're going to see that the Lipschitz trivial values is what's in between. So you get something like this. If I'm not mistaken, you get something like this. Because there are lots of symmetries, and so it's symmetries for both variables. So here you're going to have I think this is the one level. This is f minus 1 of 1. And you're going to have the other levels, they're going to be things like this. I don't know to which capacity. Yes, because of the symmetry, that might be like this. And here inside, you're going to have guys like this. All these arms, okay? So this is and blue will do. And here I have, I don't know exactly, but you're going to have, of course, as Fernando knows, if I took the gradient, I'm going to collapse into singular points. So I have 4 singular points. And so this is it. And so you see, you get a polynomial real function. You have compact levels. You have a transition, boom. And then you have non-compact. So everything's possible. So that doesn't answer your question, but at least it's a nice picture. Also, I think. Okay. So a general remark, which is really a stupid property of combining topology and differential calculus, is just that if you have let's not bother about the regularity, differentiable impact. And here you get an interval over which it is proper. F is proper. Let's put it this way. Over AB. Then if this is just really differentiable calculus, is nowhere dense in AB. So you don't have accumulation of critical values. That's what it means. Then every values which is regular level is compact. Okay. So if I take a connected component, let's say I take alpha, beta, a connected component of this, then this guy is compact. And I have local triviality over which. So I get a diffeomorphism over a compact domain, which is infinity, for instance. So it's going to be Lipschitz, because I have an infinity many local Lipschitz constant. So there is a large one. So this because of this property of differential topology, this result is absolutely not surprising. Whenever I got regular proper values, I'm necessarily immediately a Lipschitz trivial value. And what the theorem says that for polynomials, there is no other. So now I'm just going to yeah. So what I want to talk, maybe I'll talk the corollary afterwards. I just want to single out 2 facts why the result is true. So, oh, that's a shame. Okay. So why does it work? Why such a statement? Clues or ingredients. Let's put it this way.
Sorry.
Yes.
But in this example, how can you reduce f?
Now it's already
One
reduced.
variable. I mean, what is g in this example?
G equal f. Now this is not to illustrate it's allowed whenever I have compact levels. G equal f. I can change the coordinates just for the sake of it. It's what
G goes from km to kp.
yes, and here
Usually m is equal to p.
no. Here p equals 1. And I am not in the complex case. I am saying that what I wanted to illustrate, wanted to give a non-trivial real example where you have compact fibers and non-compact fibers.
Yeah.
And if you have compact fibers, you have Lipschitz trivial values by this argument. You just push the gradient, as you know, you're going to trivialize. That's how you're going to trivialize. This is one trivialization. And this one's going to be even analytic. So, but this is just to illustrate the fact that in the real case, you have a far more subtle, flexible setting than in the complex one. The complex one is just you just have finite mappings which may admit, or suspension of finite mappings which may admit Lipschitz trivial values. None others, nothing else. The real case say, no, my friend, it's much more. If you cut badly the complex world, like here, then those Lipschitz trivial values can leave. Some may be Lipschitz trivial values, and there will be properness values, and some others will be non-properness values and non-Lipschitz. And that's the dichotomy that is in this result for the real case.
So this example taken in the complex.
No, I didn't. I don't know.
You have not
There's
trivial Lipschitz value. Or
there aren't any. In the complex case, there aren't any. I cannot reduce this polynomial by this trick to a polynomial in one variable. So this complex polynomial has no Lipschitz trivial values.
Yeah.
0, empty. This is that's one corollary I didn't want to talk about. But so okay, if I have time, I say a few words about this. But I'd like to point out 2 clues. Okay, so the first clue is if you pick the definition over there, or which I suppose is just actually here. Okay, so the definition I want is here. The definition about Lipschitz trivial values. What is going to tell you, because of this Lipschitz map, if I pick 2 different levels here, it's going to be that the distance between them is non-zero. That's going to mean, so if I take C in LF, Lipschitz trivial values, and I will assume that this guy is not empty. So there is this neighborhood V, over which I have the Lipschitz realization, and I pick 2 guys in there. Then what I will obtain, that's the distance between the level, so in Km, so there is a constant here. So you have 2 levels of a polynomial map which are far away from each other. And this is, as I explained, just when you think about it, start to find example, and then after lots of, you say, oh, parallel affine subspaces. But do that. Are there others? No, I can't find any others. And the theorem say, yeah, you better not find any others. If you find any others, yeah, the theorem is wrong. That is possibility. But the proof is so simple that it's a very unlikely. And okay, so let's look at examples of mappings where the fibers can be far away from each other. So I'm going to start to look at, I could make some, of course I will not, anyway. So let's look at this one. I know it's not quite a polynomial mapping. It's almost a rational map, but it's a certainly smooth and semi-algebraic map. Okay, so it's a very good map in terms of behaviors. And the reason of this is just if you look at the level, well, you're going to have at infinity. At infinity, it's almost something like this. So I have two. So here I have infinity. So this is the sphere at infinity. And I'm going to have lambda here. So I'm going to have something. I got this asymptotic direction. And my level here, this guy here, is going to come this way. Because these are graphs of function. Y equal lambda of something. So they are very. I'm going to come here. And I'm going to connect here. So yeah, there may be critical. There's no critical point in here. And I always have dy of f, which is positive. So which is so no critical point. And whenever I have different lambdas, well, I think it's like this, but if it's not like this, that's the other way around. Doesn't matter. There are 2 points at infinity. Whenever lambdas varies, the endpoints varies, and okay, this is for lambda prime. This is for lambda. And from the metric point of view, the distance between these two guys here is infinity. And the distance goes with the angle between these two points. The angle times the radius plus something small. So they are the fiber of those maps, when I go to infinity, they are very far from each other. Okay. Yet, this map has no Lipschitz trivial values. So this phenomenon as infinity is too much. Okay. I'll give an argument in the next 15 minutes. I'm going to need 2 or 3 more minutes. So another map now, which is going to be polynomial. It's going to be 3 variables. X, xy plus z. Well, if you see that all the levels, so let's call it G or phi. So phi of AB is just an affine line. Okay. But those affine lines are not parallel. If you cut in the place x equal a, you see x equal a, you see, in the plane they are the same, they are the level of this map, but you change the plane, the term, with a over b. So again, those fibers, those lines, when you look at infinity any two, the distance tends to infinity. You can check. You can do the computation of these. You're going to get this. And now I need a final board to give which would it be? Yes, that's going to be this one. No. And there is a lemma. The lemma is the following. Let's say, and which is not true for polynomial mapping. It's true for Lipschitz trivial value. So for this schema, this definition. And it says, so suppose that phi is Lipschitz trivial values of 5. Okay, and you can do this in metric spaces. It's exactly it's going to be true as well. Then there exists. Sorry. There exists V, a neighborhood of C. I'm working in KP, but it doesn't matter. And 2 radius. What's that? The epsilon tube around F minus 1 of C is contained in the pre-image of V, which is contained in the delta tube around. And where the tube is just as before. Yes, it's just. Okay. So those 2 examples here do not satisfy this, because those levels, they get out of any tube around this one. I just have, here I have a tube like this. So here I get space, but at infinity, it's very thin from the point of view at infinity. It's very thin. And since you go accumulate at other points, you are not contained in this tube. And with these two obvious ingredients, you can prove the results. You can kill off variables. Just a comment on it. So we thought, okay, we're going to do like in the first result about functions. We're going to do an induction. So we managed to kill off a variable up to the point that we never managed to produce the Lipschitz homomorphism at the lower level, because we know nothing about this homomorphism. It just that exists. And if you cut by hyperplane or anything, you don't know if what you have is still a homomorphism, even Lipschitz one. So we had to have another strategy, and that's when appear this x infinity and this dimension. I'm going to stop here. Thank you.
Thank you very much. Any questions or comments?